Greenland is melting. Satellite images of Greenland from space show the enormous white ice sheet covering the island with dark meltwater pools visible on the surface. In 2024, Greenland lost approximately 280 billion tons of ice. 280 billion tons. In 1 year. The Arctic sea ice that covers the Arctic Ocean every winter is shrinking at approximately 13% per decade since satellite records began in 1979. Glaciers in the Alps are retreating up mountain slopes, leaving bare gray rock where ice once stood. Himalayan glaciers that supply fresh water to over 1 billion people across South Asia are thinning and receding. Andean glaciers in South America that supply water to Lima, La Paz, and other cities are disappearing faster than they can be replenished. The Intergovernmental Panel on Climate Change confirmed that 36% of today's mountain glacier mass is already committed to be lost, regardless of what we do about emissions now. Everywhere you look on Earth where there was ice, there is now less of it. And the question that most geography and science videos never fully answer is the simplest one. Why? Not why are temperatures rising in general, but specifically why does warming cause the Arctic to lose ice so much faster than the rest of the planet? Why does the loss of that ice make warming accelerate further? And why does everything connect the melting Arctic to European weather, to the Asian monsoon, to sea levels threatening cities built by ancient rivers? Today, Where on Earth explains the geography of why the ice is melting. Simply, completely, from the beginning. Subscribe to Where on Earth and hit the bell. Now let us start with the most fundamental question. Why is the Earth warming at all? The sun sends energy toward Earth as solar radiation, visible light, and infrared radiation crossing the 150 million kilometers of space between them. When that solar radiation reaches Earth, some of it is reflected back into space, and some is absorbed by the surface and atmosphere. The Earth needs to radiate back into space as much energy as it receives from the sun. If the Earth is absorbing more energy than it is radiating back into space, the planet warms. If it is radiating more than it absorbs, the planet cools. The balance between incoming and outgoing energy determines the temperature of the planet. Carbon dioxide in the atmosphere acts as an insulating layer. Carbon dioxide molecules absorb infrared radiation that the Earth's surface radiates outward. They then re-emit that radiation in all directions, including back toward the surface. This process traps heat in the lower atmosphere. It is called the greenhouse effect. It is not new. Without any greenhouse effect, the Earth's average surface temperature would be approximately minus 18 degrees Celsius, cold enough to freeze the entire surface of the planet. The natural greenhouse effect maintained by water vapor, carbon dioxide, methane, and other gases keeps the planet at an average of approximately plus 15 degrees Celsius, warm enough for liquid water, for life, for every civilization that has ever existed. Human activity since the Industrial Revolution has added approximately 50% more carbon dioxide to the atmosphere than existed before industrialization. Atmospheric CO2 reached a new record high in 2025 at 152% of 1750 levels. More CO2 in the atmosphere means more heat trapped. More heat trapped means higher surface temperatures. Higher surface temperatures mean ice melts. This is the basic mechanism. Now let us understand why the Arctic warms so much faster than everywhere else. The Arctic Ocean is covered in sea ice, frozen ocean water that reflects sunlight back into space. Fresh white snow covering sea ice in the Arctic has an albedo of approximately 80 to 90%. That means 80 to 90% of the solar energy arriving at that white surface is reflected straight back into space. Only 10 to 20% is absorbed. The dark open ocean water exposed when sea ice melts has an albedo of approximately 6%. 6%. That means 94% of solar energy arriving at dark open ocean water is absorbed. Only 6% is reflected back into space. Now imagine what happens when rising temperatures begin to melt Arctic sea ice. Ice melts. Where there was white ice reflecting 90% of solar energy, there is now dark water absorbing 94%. The dark water absorbs more heat than the ice it replaced. More heat warms the water and air further. More warmth melts more ice at the edges. More melted ice exposes more dark water. More dark water absorbs more heat melts more ice. The loop feeds itself. This is called the ice albedo feedback loop, or more simply, the albedo effect. It is the primary reason why the Arctic warms nearly 4 times faster than the global average. Some areas of the Arctic near the Barents Sea between Norway and Russia have warmed up to 7 times faster than the global average since records began. 7 times faster. In the same period that the average temperature of the Earth has risen by approximately 1.2 degrees Celsius, the Arctic has warmed by approximately 4 to 5 degrees Celsius in many areas. The Arctic is not experiencing what the rest of the planet is experiencing. It is experiencing something dramatically more intense, driven by the Albedo feedback loop. Now let us understand the different types of ice and why they matter differently. A diagram shows the difference between sea ice floating on the ocean and glacial ice sitting on land above the ocean. There are two fundamentally different types of ice in the climate system. Sea ice is frozen ocean water. It floats on the surface of the Arctic Ocean. When it melts, it does not directly raise sea levels because it was already floating in the ocean. Like ice cubes melting in a glass of water, the water level does not change. But melting Arctic sea ice does enormous damage to the climate system through the albedo effect. Less sea ice means more dark ocean surface absorbing more heat. More heat means faster warming of the Arctic. Faster warming of the Arctic changes the behavior of the jet stream, the atmospheric current that steers weather systems across the northern hemisphere. A weaker temperature contrast between the Arctic and the tropics weakens the jet stream. A weaker jet stream becomes more wavy and less consistent. It takes longer loops north and south instead of flowing consistently east. Weather systems get stuck in position for longer. Heat waves last longer in summer. Cold snaps last longer in winter. Droughts persist longer. Floods are more intense. The melting of Arctic sea ice does not just affect the Arctic. It affects the weather experienced by everyone in the northern hemisphere. Land ice is different. Glaciers and ice sheets sitting on land above sea level. When land ice melts, the meltwater flows into the ocean, and sea levels rise. Greenland is the largest single source of land ice loss on Earth. Greenland lost approximately 280 billion tons of ice per year in recent years. Each 280 billion tons of ice lost raises global sea levels by approximately 0.8 millimeters. That seems tiny, but compounded over years and decades, it adds up to centimeters of sea level rise. And the rate is accelerating. Antarctica contains even more land ice than Greenland. The West Antarctic ice sheet alone contains enough ice to raise sea levels by approximately 3 to 5 meters if it collapsed. The full Antarctic ice sheet contains enough ice to raise sea levels by approximately 58 meters. Scientists have confirmed that parts of the West Antarctic ice sheet have already crossed tipping points. The grounding lines, the edges where the ice sheet meets the ocean floor, are retreating inland. Once those grounding lines retreat beyond certain geographic thresholds, the ice above them becomes unstable and can collapse rapidly. The geography of Antarctica's bedrock matters enormously. Large portions of West Antarctica sit in a geographic bowl bedrock that slopes downward inland. As warming ocean water erodes the ice from below and the grounding lines retreat, they enter deeper water. Deeper water means more ice is exposed to warm ocean water. More exposure means faster melting. Faster melting means more retreat, a self-reinforcing collapse that could be irreversible on human timescales. Now let us understand what happens to the rest of the world when the ice melts. Mountain glaciers cover approximately 10% of Earth's land surface outside of Greenland and Antarctica. Mountain glaciers in the Himalayas feed the Ganges, Brahmaputra, Indus Yellow, and Yangtze rivers. Those rivers supply fresh water for drinking agriculture and industry to approximately 2 billion people across South and East Asia. As Himalayan glaciers retreat, they initially release more meltwater as the ice melts faster than it accumulates. River flows temporarily increase, then the glaciers become too small to maintain even that increased flow. Rivers that depended on glacier meltwater begin to run lower in summer. Eventually much lower. The geography of glacier-fed rivers in the Himalayas is the geography of water security for 1/4 of humanity, and it is changing. Glaciers in the Andes supply water to cities including Lima in Peru with a population of 11 million people. As Andean glaciers retreat, water supply to Lima and other Andean cities faces increasing stress. European glaciers in the Alps supply fresh water to the Rhine-Danube and Rhone rivers. Those rivers feed agriculture industry and populations across Switzerland, France, Germany, and Austria. The glaciers feeding them have retreated dramatically in the last 50 years. Now let us understand the second feedback loop that makes melting ice so alarming. The permafrost beneath the Arctic landscape stores enormous quantities of carbon. Permafrost is frozen ground that has remained below 0 degrees Celsius for at least 2 years. It underlies approximately 25% of the northern hemisphere's land surface. The organic material frozen in permafrost. Dead plants, animals, and microorganisms preserved by the cold contains approximately twice the carbon currently in Earth's entire atmosphere. Twice. As the Arctic warms and permafrost thaws, that organic material begins to decompose. Decomposition releases carbon dioxide and methane. Methane is approximately 80 times more powerful as a greenhouse gas than carbon dioxide over a 20-year period. The release of permafrost methane adds a second wave of warming on top of the first. More atmospheric greenhouse gases trap more heat. More heat warms the Arctic further. More warming thaws more permafrost. More permafrost releases more methane, the second feedback loop feeding the first. A study published in April 2026 found that as Arctic permafrost thaws, it is reshaping rivers and releasing vast amounts of ancient carbon that had been locked away for thousands of years. The permafrost feedback loop has the potential to add warming that human emissions reductions cannot reverse. Because once the permafrost starts thawing on a large scale, the release of carbon continues regardless of what happens to industrial emissions. Now let us understand how melting ice connects to everything else in this series. Greenland meltwater pouring into the North Atlantic disrupts the Atlantic meridional overturning circulation, and that current helps keep Europe warm. Rising sea levels are threatening the river deltas we covered, like the Nile Delta that built ancient Egypt and the Mekong Delta that feeds 200 million people. The Ganges Delta is also at risk, where big cities like Kolkata and Dhaka are sinking. Melting glaciers are reducing the fresh water supply for the billion people who depend on glacier-fed rivers across Asia and South America. Permafrost thaw is adding carbon to the atmosphere that amplifies every other effect. Arctic sea ice loss is destabilizing the jet stream, creating more extreme weather across the entire northern hemisphere. The melting ice is not an isolated event in a remote location that does not affect the rest of the world. It is the trigger for a cascade of geographic consequences that connect the Arctic to your weather, to your food supply, to the city where you live. The Earth has experienced ice ages and warm periods many times in its history. Natural orbital cycles have caused ice sheets to advance and retreat over hundreds of thousands of years. What is different now is speed. The rate of warming happening today is far faster than anything in the geological record that did not involve a catastrophic event, like a meteor impact or supervolcano eruption. The Earth warmed approximately 4 to 7 degrees Celsius as it came out of the last ice age. That transition took approximately 5,000 to 10,000 years. The warming projected for this century is potentially 2 to 4 degrees Celsius in 100 years, 50 to 100 times faster. Ecosystems that adapted to change over thousands of years must now adapt in decades. Ice sheets that built up over millennia are melting in centuries. The geography of ice has defined where people live. It has determined which rivers flow. It has shaped which coastlines are habitable. It has decided which seas are navigable for human civilization. And it is changing faster than any natural process in our geological history. The ice is not just melting, it is triggering a chain reaction that connects every part of the planet. Understanding the geography of that chain reaction is the first step toward understanding the world we are creating. Subscribe to Where on Earth for weekly geography that reveals the forces reshaping our planet. Hit the bell and drop your thoughts in the comments below, because the world looks very different when you understand the geography of the ice that is disappearing.